the derivation basically consider two frames, right? The X, Y, Z. I mean, Jackson likes to use along Z, but I mean, at first doesn't matter. So you have this K frame and then K prime frames, and they are moving relative to one another. But at first, the first step is a general consideration first. The only constraint is that, like at t equals 0, x is x equals 0. The origin of the occupied plane is the same. It's the same as x prime equals 0. So basically, the two coordinate system, at least at the point of the origin, is at the same location. Basically, the k prime is moving relative to k. It just happened that at the t equals 0, the origin of k prime is exactly at exactly the same location as the x prime plane. Okay, so that's the starting point. We define like that, and one convenience that once you make this choice of your basically the choice of your coordinate system and the origin of your time, and that make transformation between the two frames, what we call the linear transformation. You don't need to do a translation. You just everything is linear. Okay, and now the idea is that at t equals 0, you just turn on a certain light source. That's a flash. Okay, and then this light source obviously will propagate away. So then at time t, then the location of this light circle will propagate from the origin, right? So basically, the radius of this circle, or this actually spherical surface, should be c times t, right? Because at time t, it propagate a distance c times t over it, right? So so that is in the K frame. But then the postulate of the two postulates, we assume that the relativity, the speed of light is the same as in both frames. So in that case, in the K prime frame, in this same speed, same surface should be the same as the surface that with the radius t prime, and the same location should be the absolute relative, whatever the frame that you're looking at is still the same surface in the space time, whether you're looking at K frame or K prime frame, should be the same sphere. It's just, I mean, it propagate away. Then you observe, although the coordinate x, y, z, and t may change according to the frame, but the location of the surface is not the should be the same. So, and this location is the radius is ct, means that the distance on the surface the distance from the surface to the origin is the same as ct. So you can say c squared t squared minus the distance is x squared. You can say x squared minus y squared. I mean, you can do it different signs. I think like follow Jackson's way of writing it. But this one is the location of the sphere, light sphere in the K frame. So this one must be the same as the same location on the in the K prime frame. And right? Assuming you have some relative velocity between them, but in this case, this relative velocity v is at first is arbitrary, whatever that constant velocity vector is, that the same arguments still apply. So in order to express that, these two should proportionate each other, so this quantity would be a factor, and this factor should be positive actually, because this, although on the surface it's zero, but say within the surface, within the light surface, or in the interior of the light sphere, then this quantity will be less than zero, or will be positive, because at this distance is less than ct. So ct squared minus this one should be positive. And likewise, the point inside the light sphere, which means the light has already passed this point. And this is an absolute event, whether the light passing any certain point, whether you observe in the K frame or K prime frame, should not matter. This is just, whatever happened is happened, whatever not happened is not happened, right? So whatever frame you observe should be absolute. So if a point is interior to the light sphere, should be the same in K prime. So both should conclude that it's interior. So when one is positive, the other must be positive. So this is a positive number. Okay, so that is, so get stable is lambda square. And so now the idea is that the lambda square, and obviously not depends on the coordinate, but it can, in principle, at least as a matter of argument, it depends on the vector. But then now if you think about the situation, this you can add an assumption. This is basically an assumption of our space, and if you assume the space is isotropic and everywhere, every direction is the same, and there's no preferred direction. So therefore, whatever the velocity you choose, so what means that whatever the k frame, as long as it's moving with a certain speed relative to uh, the the k prime relative to k, same speed, the same argument should apply. So the orientation of the velocity should not matter. So that you can get rid of this vector and say that this should just depends on the magnitude of the velocity, relative velocity. Okay, and so assuming that that is true, then you apply the same relationship again. So because k pi is moving with velocity v relative to k, and then you can also say k is moving in velocity minus v versus relative to k prime. So we apply again. So I think I might have missed. I mean, all I think Jackson wrote k prime here, t here. Doesn't matter whether it's prime or non-prime, but you apply again, so this becomes lambda square and another lambda square, and this is supposedly minus v, but then we already argued that it should not depend on the direction. So you're going back to the same expression on both left hand side and right hand side, and then because this relation is valid for any x, y, z, t, so you can actually conclude that this must be 1. So this lambda 4 v is 1. Okay, so obviously lambda square will be 1 because we are already assumed that it is positive, so it cannot be negative 1. So in this case, we can actually get rid of the lambda square now. Okay, so basically, the first argument is saying that after all these arguments, this is true. So as long as we have this choice that the two origin is at the same location at t equals 0, then this equation is valid. Okay, so transformation must preserve this relation. And there's a name for this one. If we call this as space-time coordinate org, we form what we call a 4-vector. This will be the norm of the 4-vector, the norm of the square of the norm of the 4-vector. So the 4-vector in here is CT, and then XYZ vector, you can say just write symbolically as the usual spatial vector. So this forms a time part, and then the spatial part of the vector, and then the norm or the square of the norm, depends on how you say the norms. So the norm will, according to this, is c squared t squared minus x squared. And some convention choose it the opposite, x squared minus c squared t squared. That also. So it's what I'm saying is that this is invariant. So whatever frame you measure that, this should be invariant. So in the K frame is like that, in K prime frame is like that, but it should be the same. Once you whatever transformation that we finally derive should preserve the norm. Okay, after we do that, the transformation, we see that it will do this. Will satisfy this condition. All right. So that is the first step. The second step is now instead of considering arbitrary mean, we restrict ourselves to just a relative velocity according to one of the coordinate, one of the axes. And Jackson just choose if the velocity is in the z direction. Okay, so the relative velocity in z direction is that. That's fine, right? Now, because actually if you have arbitrary direction, the Lorentz transformation will become very complicated. So we simplify that. And one great simplification is that by this choice is Alonzi, you can make the assumption that this transformation must preserve the x prime and the perpendicular coordinate because we assume that the perpendicular direction is not affected by this relative velocity along the z. Okay, so the transformation will preserve x prime goes to x and y prime goes to y. Okay, so that is just for the particular choice. This is general. Whatever frame you transform must satisfy that. But for the restricted case, as the relative velocity is around z, the perpendicular coordinate doesn't change. Okay, so in that case, for this restricted case, then you can subtract off this two. You can write. I see. Doesn't actually have that, so we just subtract it off. C squared t squared. C squared equals c squared t prime squared minus t prime squared. Okay, so that is this case. Now to be even more specific, instead of just this is like this represents 2 points. I mean, when this 0 represents the light speed at the forward direction and the backward direction, a positive c and negative c. Now we are doing a more specific consideration. So you consider just the forward directions. If you have the same light source that propagate along the z direction only, consider this point, right? And obviously, this at this point is basically c. This is ct. At the k frame is ct minus c equals 0, right? So this point is ct minus 0. But the same consideration in the k prime frame, you also should also conclude that this point, the location of this light speed along the z direction, along the relative velocity direction, should also satisfy this ct prime minus c prime must be equal to 0. Okay. So again, to use the same argument, so ct prime minus c prime must be proportional to, there will be two of them, so lambda 1 ct minus c. And we can also argue that lambda 1 must be positive, just like what we argued that what I already erased is the lambda square. That is because it just separated whether the c value, whether the light already passed you or the light or not already haven't reached you yet. So that should be positive. But in the derivation, that's not that important. So I just leave it like that. Okay. So this is true for the positive C1. But negative C1, you can do the same argument and conclude that you have another equation. Now, instead of CT minus C is 0, it becomes CT plus C equals 0. Okay, so this is plus C prime equals to lambda 2 CT plus C. Okay, and then so you have two equations, then you can multiply the two equations together and get c squared t prime squared minus c prime squared equals to lambda 1 times d squared t squared minus c squared. Okay. Now to compare this with what we conclude before. This is this two equals with the proportionality constant is 1. So this implies the lambda 1 times lambda 2 1. Okay, so that fixed one relation that we'll use later. Now you have these two equations. You can solve this, solve the relationship between t prime and t. You already have the relationship between x prime and x and y prime and y, which are trivial. But so we need the transformation between these two values. So t prime, c prime in terms of tz, and the inverse is just trivial. But let's just solve it first. So to get t prime, there's two equations. Basically, add the two equations, you cancel t prime, you get this add together. So you can write it as a matrix now. Let's see t prime, c prime. So obviously, it's this to add together. Lambda 1 plus lambda 2 over 2. Because add together, you have a factor of 2 here divided by 2. And that is CT, right? And so that, and then it's for this one is minus lambda 1 minus 2 because you have a minus. So this minus number one minus times C. That's T prime or CT prime. For C prime now is you subtract the two. When you subtract the two, cancel with this two, you get a minus two as you divide by minus two. So for for this part is subtract the minus x lambda one minus two divided by minus two is this one. And for the C prime is minus minus become plus, and divided minus two is just the same. And the one plus number two. Right? You see what I'm doing? So this basically solve the two linear equations and get this matrix equation. So that is in the form of a transformation. And so you can do one more simplification. And it's not a simplification, just make it instead of writing that many terms. Just simplify your writing. So A would be this one, B would be this one without any difference. So, yeah. Okay, so it just simplify your writing, doesn't matter. Okay, and now you need two conditions to find this two value A and B, or lambda one, lambda two. It depends on how you look at it. Okay, and you already have one condition because lambda one times lambda two is one, so you need one more condition to fix that. And the condition is the easiest one is that the two coordinate system at the like the origin of the K-prime system, K-prime frame is C prime equals 0. This is the origin, right? This is going through the origin of the K-frame at t equals 0, and then continue moving along the Z direction. And the fact that it's moving with the relative velocity v means that this point C prime equals 0 it's the same when you observe in K prime is C equals Vt. So this point is moving according to this equation when observing K frame. So this point must transform to Z and T that satisfies this given. Okay, so let's use that. So when C prime is 0, so this is CT prime. CT prime and C prime, and this is 0. You need to satisfy this. The C prime or 0 must be equal to minus B and CT plus A times Z, which should be the same as this one. So this is, or you solve this. This is C equal to Vt, right? So this for this equation, C is B over A times CT, right? So it means that this is your V, right? So it means A is the whole thing is V. A is V. This B times the whole thing is V. This is V, right? V equals to BC over A. Or, I mean, the ratio B over A is V over C, which we define as a parameter beta. Okay, in that case, you can express B as beta times A. The ratio is beta, so B is beta times A. Okay, so that's another condition. Now you can put it back to here. Lambda 1, lambda 2 equals to 1, and then obviously you need to solve for 101 lambda 2 in terms of A and B, and that should not be difficult because A is this one, right? B is this one without the negative sign. Right? So obviously, uh, in terms of lambda, in terms of A and B must be, so if you have A plus B, we cancel the lambda 2 terms and only lambda 1 term. So, right? So that way, A plus B will give you just lambda 1. Right? You add the 2 without this negative sign. Add to that. Right? So this cancel lambda 2. Okay, so that's not too bad. And then A minus B, A minus this one, now instead of getting rid of lambda, now you get rid of lambda 1 and only lambda 2. That's left A minus B lambda 2. Okay, and so lambda 1 times lambda 2 is A plus B times A minus B is A squared minus B squared. And B is beta A, so it's A squared 1 minus beta squared. Okay, that equals to 1. This means A squared is 1 over 1 minus beta squared. Okay, and so we'll choose the positive root, which is for the obvious reason. And later on, you also argue that because number 1 and number 2 positive, you see that in order to get both and positive, is both A and B are positive. So A is chosen as a positive root, so it's 1 over 1 minus beta squared. And later on, we actually define this as gamma factor. We call that the relativistic factor or Lorentz factor. Okay, that's which is commonly used in relativity and then actually part of the Lorentz transformation. Okay, so A is gamma, and this means B is gamma times beta. Okay, so we are done with the derivation, so we just write B is gamma. B is gamma, beta is minus gamma times beta, minus gamma beta. Gamma. Yeah. Okay, so this is the final form of your Lorentz transformation. The T pi and C pi is transformed from CT by this transformation. It's okay, so that's at least one way to divide it, and there are many ways, and there are people using graphical, also using graphical method to divide that, and that not too bad. That actually can be done. Okay, so likewise, of course, you can do the inverse transformation CT. Obviously, you can invert the matrix and just multiply the invert matrix, and that is obvious. Actually, not too difficult to do. But another way to do it is obviously K is relative to K prime by minus V. The K is relative to minus V versus K prime. You can just change the sign of V or change the sign of beta. So this becomes beta. Okay. And now this is actually the end point. You can say that this is end result. And but as a matter of just completeness, you can also solve for number 1, number 2. So number 1 now is this is gamma beta. gamma 1 minus beta. And obviously beta is more than one, and later on we'll argue that velocity of particle or basically any material cannot be larger than the speed of light. So beta is v over c. If v is less than c, so beta is less than 1. So 1 minus beta is positive. Gamma is chosen to be positive, so this is greater than c, just like what we assumed. And also lambda 2 will be, whether gamma, actually lambda 1 is 1 plus beta. Right. Gamma 2 is 1 minus, but both will be greater than c. Is that okay? So that finished.